let's say two vectors U and V. So we start with two vectors in. Okay, so you can just assume that U equals to, let's call them U1 or UX, U1, U2, U3, which can also be interpreted using the unit vectors we agreed upon earlier. So I can say that this is U1 in the ith direction plus U2J plus U3K. So from now on, I'm going to drop this hat on top of them with the vectors here. So just I, J, and K are, bear in mind, they are the unit vectors in each direction. So either this way of writing the vector or that way, it will break down its components to the three different coordinates. So here, similarly, V1, V2, V3 are the coordinates of vector V. And here you can just break it down as the J plus V3. Okay, now we will learn how to evaluate. Now, U cross V equals to. Now, if you are not familiar to the determinants at this stage, don't worry. So these two vertical bars are representing what we call a determinant. And a determinant, it's just as the name indicates, it determines a value for a square matrix. Now here, what we do is, in the first row here, we just place the vectors I, J, and K, the unit vectors, okay? In the second here, I just place the coordinates of the vectors, so U2, U3, V1, V2, V3. Okay? And this is determinant. This is a determinant. And this determinant, evaluating such determinants, believe me, it will play a very, very central role in this section and beyond. Also, when we talk about linear, evaluating solving linear systems and so on. Now, what is a determinant? Anyone who never heard about determinants? Determinants, guys online, did you hear about determinants? What is a determinant? Guys online, I don't see anything on the chat, so yes or no? Can you hear me? Anyone here in the classroom who never heard about determinants? What is it? Who? You never heard about determinants? Okay. Now, determinants are closely related to a square matrix. Did you hear about matrices? Yeah. Okay. Matrices, they are just, later we will be having, when we talk about solving linear system, very detailed or in depth, actually, information about determinants. Matrices are simply, you can think about it, arranging elements in some so let me just here determinant of a square matrix. By now, a matrix is just an arrangement of rectangular arrangement of numbers or values in columns and rows. This is all you need to know. Number of columns and number of rows is equal. This is what we call square matrix. So when we talk about determinants, it doesn't make any sense if we talk about determinant of other dimension than same number of columns and rows. This is number one, okay? The concept of square matrix is clear. Okay, so let me just take a 3 by 3 matrix A, B, C, D, E, F, G, H, I. I hope I still recognize the alphabet. So is that correct?
Yeah.
Okay, so this is now I don't want to go in depth of the Leibniz theory of evaluating the determinants. Now, determinants usually they are evaluated using what we call in computer science recursive algorithms. That means algorithms that the function evaluates itself in a smaller, let's say, parameter. Okay, that means here if we have such determinant, of course it will be for n times n. That means in each step you will just cancel one row and one column to get a smaller determinant. Is it clear what's meant with the recursive? So you just reduce it until you get, always I tell you about this Russian figure, I don't know how it's called, something like that. So you have things incubated within each other. So you just, if you cancel one row, one column, obviously you will be getting, if you start with n, let's say 5 times 5. If you cancel one row, one column, you will be getting a 4 by 4 matrix. If you again apply it, cancel one column, one row, you will be getting 3 by 3 up to 2 by 2. Then the algorithm will terminate and it will calculate the result. So this is the general idea about Leibniz determinant. Now another thing here, it's not only recursive, it is alternating. What does it mean alternating? It means once it's negative, once it's positive. Positive, negative, positive, negative, positive, negative. That means in mathematics, when we want to distinguish this operation, we just use something like powers of n, where n is odd or n is even. I don't know whether you can realize that if you have -1 to a power odd, it will result in -1, right? -1 to power even, it will be even number, right? So in mathematics, they just odd, they write it as 2n plus 1. Even is just 2n. So 2n, that means, well, n is natural number. So 2n plus 1 will, if n is 0, it will generate 1. If n is 1, will generate 3, and so on. So this is another way of writing odd, which you think about it, it will generate 1, 3, 5, 7, etc., and so on. So now, for now, since we are talking about 3 by 3, it's enough not to go in depth in this complex, let's say, procedure. You need to know that this alternating starts with positive, then negative, then positive. I'm talking about the columns here, positive, negative, positive. Okay, this is all you need to know. That the first column is positive, second column is negative, third column is positive. Okay. Now, what else we need to know? We need to know that for 2 by 2 determinants, the determinant of A, B, C, D is equal to A, D minus C, D. So it's just this diagonal, multiply it out, minus this diagonal. Now this here is going to be our termination. Everyone understands what's a determination? Termination? To finish, yeah. It's just like you are just wrapping up this metochka, then you get in the term, the last piece that you can't go further, okay? Now here, if you notice, if I'm going to apply this method, so cancel one row, one column, until I get to this form of 2 by 2 determinants, then I will use this equation. Okay? Is this clear?
Yes.
Okay, now let's go to this matrix again, and we will evaluate the determinant of this matrix. Now the algorithm, so here this simple algorithm, or the simple case of the algorithm, important here is this alternation plus minus. The method is as follows. We will start, of course, later we will see that you can do this calculation according to any row or column. But since here, remember, bear in mind, we have I, J, and K here. So we will go and evaluate it according to the first row. Okay. Now what we do here, I will take this element, A, and then I will cancel this row and this column where A is located. It's just like you just take this and you cancel them. Now notice here in the middle, I'm left with a 2 by 2 determinant. So I multiply A with this 2 by 2 determinant. This is number. Okay. Is it clear so far? Yeah. So A, and then I will just write the determinant E, F, H, I. Now here in the middle, I have a negative. Don't forget. Now here I will do the same. I have negative B. Then what is left if I just... Okay, so I will left with the 2 by 2 determinant D, F, G, I, right? And the last one I have here is C, C, right? Plus C times here I'm left with D, E, G, H. I'm almost done. Since here I know this rule here, let me just frame it, this one here in the middle. I know this rule, how to evaluate a 2 by 2. So this is how recursive works. So at the end, you know the rule to evaluate this kernel here, and then we just apply it. Okay. So then I'm left with, so evaluating the determinant again, this diagonal multiply it out minus this diagonal. Okay. This diagonal minus this diagonal. This diagonal minus this diagonal. One common error here is if you have a minus from the formula, if you have a negative here, some students are mixed up. So just I advise you always to use parentheses. Okay. So let's evaluate it. So A times AI times HF minus, sorry, HF minus P times DI minus GF, and the last one here C DH minus GE. Okay, then you can of course expand it. So this is the final formula. This is one way how to do it. Now notice here a very important thing, that if I multiply or construct the cross product of two vectors, we said I'm going to get a vector. Now if you look at this notation here, at the end here, what is A, B, and C? They are I, J, and K. So here at the end you will be getting a component in J, component in I, and component in J. Yes, please, go ahead.
The why between the parentheses is EI minus HF. Why exactly?
Because it's from the formula for evaluating a 2 by 2 determinant. It is a rule for evaluating a 2 by 2 determinant. It's this diagonal minus this diagonal. So that's why I framed this. Okay.
Thanks.
So this is one method to evaluate the determinant. So if we want to evaluate a determinant, then we will getting, again, I was talking about here, I, J, and K. So at the end, ultimately, you will be getting a vector with 3-dimensional coordinates. Now, luckily, evaluating determinants, let me just check if the students online have any questions. Guys online, can we do what? ADG. Yes, of course you can. Yeah, you can do it, but yeah, a student is asking, is it possible to evaluate the determinant along a column, then first column, then the first row? Of course you can, but here, and when we're talking about vectors, sorry, we ultimately look for something okay, so the guy who was asking, I just want you to have a look at this, because here we are evaluating a cross product. We will be doing this according to the first column, first row, sorry, when it comes to evaluating cross product. This is an important question, but in general, if you have a determinant in any other context other than cross product of vectors, you can do it actually not only according to this column, but also according to any row or column. You will be getting the same answer. Okay, but when we talk about cross product of vectors, please stick to using this along the first row. Is this clear? Because we want always we will place I, J, and K. So always whenever we will do an example, always when we are to evaluate, when we want to evaluate the cross product, we need to work along this. Okay, let me just mention one word about the triple product. Maybe shall we talk about the triple product, and then we will go to the triple product, and then I will elaborate more on this and demonstrate some examples. Now, the triple product is also important. Why? Now, by the way, why determinants are important? Determinants are important because they have many applications in linear algebra. I told you very often that if you just place, if you have a linear system and you place the coefficients of your linear system in a determinant and you evaluate this determinant, if it happens to be 0, then this determinant has no trivial solution. For instance, if you want to evaluate the inverse of a matrix, actually the inverse only exists if the determinant of the matrix is non-zero. Also, sometimes I have problems in this. I hope you can see it here. This figure here, this word here. Really big. Can anyone pronounce it? It's a little bit difficult, right? Just slowly. Parallel. Five. Okay. Parallel 5. Right? Parallel 5. Okay. This is nothing else than expanding. So if we have 3 vectors, we said that 2 vectors will span a parallelogram, right? Now, if I have another vector, then it will be a 3-dimensional something that will generate a volume rather than an area, right? So usually, if you have here squares, whatever, you will be doing something like a box. So this is similar here. And this is also evaluated using determinants. We'll see that this is closely related to the so-called a triple product of vectors. Okay. So triple product of vectors. Now assume we have three vectors. U, V, maybe we take here as easier A, B, because U and V look similar. So same vectors, same dimensional vectors. Okay. Then A will this result in a vector or in a scalar? What do you think? Remember. The parentheses indicate you evaluate a vector, right? So here you will be getting a vector. And will be, of course, a number, right? Number is the volume of this triple word parallelepiped whose sides are the vectors actually. So it's ultimately because here you evaluate this cross product, then you have a product which is a vector, right? Then you construct a dot product between two vectors, and ultimately you will be getting a number. Okay, so this is how this looks like. Okay, so the base here is this B and C here, and then the height is A. So this is the volume of this shape. Now, another important interpretation for this is that if the vectors, let's assume A equals A1, A2, A3, okay, and B equals B1, B2, B3, and C, C1, C2, C3. Okay, then this triple product can be evaluated. Of course, you can evaluate it as first constructing the product and then the dot product. But if you place these three vectors in a determinant, A1, A2, A3, you see here I get a 3 by 3 determinant. Okay, so this triple product is actually, if you have three vectors, you just place them in such determinant to evaluate this determinant. Moreover, this product has an interpretation. So sorry, this result has an interpretation. So if this is equal to 0, or of course it's not equal to 0. Okay, so this is equal to 0. If it's equal to 0, then A B, C, the vectors are linear dependent. If it's not equal to 0, then the vectors are linear independent. This is actually a great help. You saw that when we had an example earlier this morning with a two by two vector, it was that not complicated. You involved evaluating some equations. Now imagine if you have three vectors, it will be more difficult. So this is straightforward. If you have three vectors, you place them. I'm talking here about the three-dimensional vector. You just place them in this determinant. This determinant will evaluate the triple product, and this triple product can be interpreted according to the outcome of this determinant. If it's 0, then the vectors are linear dependent. If it is not 0, then they are linear independent. I think I have a question in the worksheet where we are going to solve together, which asks about some vectors that are linear dependent or independent. If you have the three vectors, straightforward, evaluate the determinant. So that's why evaluating the determinant is really a very crucial here. It's a crucial topic actually that we will need, as I promised you before, to elaborate more on this. Now let me just show you. Nobody can find it here. Okay, before we move to some examples, I want just to show you another way to evaluate. Where is it? Okay, so let me just show you. Just want to show you an example. So as you see here, evaluating determinants is very central topic here. Let's assume I want to evaluate the determinant. This is A equals to 1. One, negative 2, 3. Then I have 2, 0, 3 here. And then I have 1, 5, 4. So evaluate determinant. So this is now the determinant here, as you see here, the matrix, this is a square matrix, so the determinant is defined. Now, as you see here, we are using the square brackets for the matrix. Now, for the determinant, we are just using the vertical dashes. So determinant of A equals to 1, negative 2, 3. It was actually called determinant because it determines one real number for a square matrix. Okay. You want to give a try using the method we used before? Okay. So the first thing, just bear in mind, this is positive, negative, positive. Okay. Then you take this number, multiply it with this determinant. Then this negative, don't forget about this negative, multiply it with the determinant 2, 3, 1, 4, and so on. Okay, so take a couple of minutes to evaluate it. Please try it manually without calculators and tell me what you get. So guys online, You got it? That fast. So, any other results? So, the guy you said you never read about determinants. Is it clear now? What's what? So, yeah, be careful to the negative. Reduce it to a 2 by 2 determinant, then multiply it out and add. Done. What did you get? I'm getting five. I'm getting and it's 40 going seven. I'm getting 5, you're getting 10. Getting confused.
Well, yeah.
See here, we have different answers. So I deliberately actually choose this to be negative. What did you get? 45.
11.
11. Yes. 5. Wow, I didn't expect this wide range. Actually, no two of you are matching.
Yeah. There's a very big variety.
The thing is here, you have to be careful when you have multiplying negative when another negative, you will be getting a negative from the formula itself. Now let's just remember that if you have A, B, C, D, this is equal to A, D minus C, B. Okay, so this is actually, if you like, the root of all this evaluation. Now let's just interpret what. So this is equal to 1. Then I hide this row and this column. So let me just, for this one, maybe just try to cancel it with the pencil. So I will be left with this, right?
Yeah.
So this is the determinant I'm multiplying with 0, 3, 5, 4. Minus, notice here I have a minus 2. So I just enclose it in parentheses. And then what I'm left with? I will delete this one. So I'm left with 2, 3, 1, 4, right?
Oh.
Again, plus. So here now I cancel this one, that one. I am left with 2, 0, 1, 5. Okay. So 3 times 2, 0, 1, 5. Okay. Now this is the last step. Why? Because I just end up with the 2 by 2. So this is my if you like termination. This is the last step. I can't go further in reduction. Okay. So this is 1 times 0 times 4 is 0 minus 15. Okay.
Yeah.
Minus here the minus 2, it's going to be expanded for this one, so that's why I advise you to use parentheses. So this is 8 minus 3, right? Plus 3 times, again here I have 10 minus 0, which is 10. So here I simplify minus 15. Here I have minus, and here I have minus 10, right? This is 5 plus 30. So I have here minus 15 plus 40, which is 25. So I'm sure here in this middle part, most of you did the mistake, because here the negative. So don't be lazy. So just add a couple of parentheses, more or less will not do any harm. In contrary, they will help you to evaluate it correctly. Okay. So I hope it's clear for everyone what error Everyone figured out what he or she was doing wrong?
Yes. Yes.
How many got a 25? One. Plenty. Okay, now I will show you another method called the Saros method. I think this is the French. So, sorry, this is the German method. This is actually a very complicated method by Leibniz.
This is easy, but
For and it's using, I don't know, the problem is if you can't think computer science terminology, it's difficult to understand what's meant with recursive. So we programmers like recursive problems that can be solved using recursive because they are just solving themselves, you know, it's just you tell the function solve yourself with a less parameter. So it's just nice because of what we call complexity, meaning less calculation, processing time, and of course less memory. Very typical example for that is the factorial. So the factorial in computer program is just only one line. We evaluate the factorial of a number is the number times the factorial of the number minus one. And then you need something like termination. Of course, termination in computing is a very, very crucial thing. I'm sure all of you had some stage while using computer this loop, right? This loop is just because the program cannot break out and terminate either in some sort of loop or. Okay, now I will show you how this guy Saros. It only works. I hear that depending on something that we call the rank of a matrix, meaning how many independent rows or columns you have. Let's evaluate this one using this method. Okay, so Saros method. And please tell me if any one of you used this method before. So what we do here is we place the, let me just do it here, 0, 3, 1, 5, 4. Okay, let me here assume I have some hypothetical line here. I'm going to duplicate the first two rows. 1, -2, 2, 0, 1, 5. Now I will be having I hope that I just placed them correctly. So this one here.
1, 2, 4. 2, 3.
So I have here these diagonals. I hope it's clear for everyone. And other diagonal that from the right corner downwards, this diagonal. Now this Saros rule says the following: if I multiply out the elements of this right falling right up, left
Down.
down, right? Left down, right up, left down. Okay, so right up, left down. Anyway, this direction here, I multiply out the elements here, add them up in the red direction, subtracted from the elements of the green direction, again multiply out the numbers. It's for me it's easier to use this method because it doesn't involve much confusion, but it's up to you to use which method you prefer. Okay, so this is equal to 1 times 0 times 4 plus negative 2 times 3 times 1 plus 3 times 2 times 5. So this all we need to subtract from this side here. 3 times 0 times 1 plus 135 plus negative 2, 2 and 4. Okay. So let's evaluate it one by one. So this one is 0. Here I have negative 6, right?
Yep.
This one is 30. So here I have this one, negative 6 plus 30 minus here 0, 15 minus 16, minus 1, right? So it's equal to 24 plus 1 is 25. Okay, so you see here with this method, we got logically the same answer. I don't know which method you prefer, but I personally, I think this one is a little bit less confusing, no?
That easier.
This is a bit easier, right? So this method is just about duplicating the first two columns. Don't ask me why this works. Okay, it has for sure some proof there, but you are here not studying mathematics. Luckily, yes, please. Sorry, I didn't get you. Three, five. Yeah. Yeah, this is what I answered already. Honestly, I don't know the exact value, but it has to do with the rank. Rank of a matrix means later we will learn how to reduce the matrix using the so-called Gauss reduction formula. Now, the matrix usually has something that's called rank. Rank means the number of rows or columns that are linearly independent. I think if you have a 4 by 4 with rank 2, it will work. I think so. For 4 by 4 contains for specific relationship between the rows, it will work. But for 3 by 3, it works always. Okay.
This matrix is not linear dependent. Yeah.
This matrix definitely not, because you have here the determinant is non-zero. Okay, so that it's not the matrix, it's the vectors, and we started with. So this is good that your colleague reminded us with this interpretation of that one again. Remember, we started with 3 vectors. If I tell you, you see these. Assume that these are the 3 vectors, okay? So this vector here, let's say it's A equals I minus 2J plus 3K. And B equals, the second row is 2. So 2I plus 0J plus 3K. And C equals I plus 5J plus 4K. Okay? So if this interpretation of the 3 rows in these 3 vectors, we ended up of having the determinant is equal to 25, which is not equal to 0. This tells us that these vectors are not linearly dependent. They are linear independent, which is actually obvious. And a linear dependency means that you can write one as linear combination of another or the others. So this sometimes it is if this is the case, then you will be getting 0. Why? Because you will be having some common factor that will be canceling out. We will see when we talk about.
Professor,
Yes, please.
for example, if let's say A and B are linearly dependent vectors, B will be maybe twice or thrice or 4 times
Yeah.
A. Something like that. Is that what linear dependency
Exactly,
means?
exactly. That means this is exactly what linear dependency means. But it's not always that one is linear. If you have 3 vectors, it could be that one is linear combination of 2. That means it's 3 this line plus 4 the other, for instance. Okay. So sometimes you see it without evaluating the determinant, because one is obviously linear combination of another, but sometimes if it's combination of 2, it's difficult to tell. So that's why this determinant is a very, very, let's say, important factor here in this whole analysis.
One question.
Yes, please.
The vectors, they aren't rectangular to each other also. Like there's no 90-degree angle in the parallelogram.
The vectors are not perpendicular to each other.
Yeah.
Here in this calculation.
Yeah.
Yeah, what will happen if they are perpendicular to each other?
And we get a 0
When you get a 0 for
for
the cross
Dot.
product,
the
for the
scalar.
actually in this case not the vectors. If you go back to this is actually also a good point. If you go back to the triple product here, you go back to the triple product, it's this vector is not perpendicular to that one. Yeah. So what does it mean that two vectors are perpendicular to each other? It means they are in the same plane. So it means they are linearly dependent to each other. So they will be in the same plane. So the issue here, if this here as one vector is parallel to is perpendicular or orthogonal to that vector. But these two, if they are perpendicular or not, this is not a big issue. Okay.
And if the scalar product dot product would be 1, are they parallel?
If it's 1, then they are parallel. Yeah.
Okay.
If it's 1, they are parallel. If it's 0, they are perpendicular.
Yes.
Only the dot product. Okay. Any other questions? So as you see here, this factor here, this factor, or maybe this equation here, it helps us solve many things here. So this one translated into this determinant, it can tell us first of all the volume of this terrible to pronounce thing, parallel divide, I don't know. Parallel pivot. Yeah. It's too many L's and 5 P's. Anyway, the parallel pivot is its volume. That's actually spanned by these 3 vectors. Its volume is given exactly by this, the value of this determinant. So in this case, we have 25 is the volume of this parallel pivot that is spanned by these 3 vectors. Okay. Now, this has also interpretation that linear dependency between the 3 vectors, depending on its whether it's 0 or non-zero, and also it has a way to evaluate the so-called this product. By the way, there is a formula. Yeah, the back, I don't know. Yes.
Professor, why are we linking vector B with vector C? Why are we putting them in parentheses over here?
Yeah, because this product here will be evaluated first. Okay, this is important because in mathematics, I don't know. I think you studied how many operations you studied? Three, four, right? Four. And then you had the priority, something like
Yeah, both mass.
yeah.
Yeah, both mass return mass.
No, okay. Okay, so in German they say Punktvorschritt, yeah. So in German they use this notation for multiplication, this notation for division, plus and minus. Okay. So as you see here, this involves dashes, this involves dots. So the dots have the priority over the dashes. So this is how it translates. Now here, if you want to just let these operations have more priority, then you just place it in parentheses. Yeah? This is the same here. So this means this is evaluated first. But geometrically, this has an interpretation. This has the interpretation that this P and C they
Are
form
the same plane.
they are in the same plane and they form the how you call it the bases.
They form the base,
the
yeah.
floor of the parallelogram. Okay, they form the base. Okay. So the difference is, of course, if you just flip the coordinates there, you will end up of having the same volume, right? If you want to evaluate the volume of a box, if you just consider AB is the base, and then evaluate it multiplying by the height, or do it the other way around, it will
All end up with
no,
the same answer.
will come up with the same answer. Okay, so this is, I think, all I just wanted to tell you about this before we move to a new section. Any questions? Any questions? Let me see here. Okay, now we will go to another topic, which is too noisy, huh? Okay. Complex numbers. So I think this is section 1.6. Now complex numbers actually they combine. You can think about them also as a vector. We'll see there is lots of parallel behavior with vectors, in particular two-dimensional vectors. But let me remind you what complex numbers are. So complex complex numbers. The complex or imaginary numbers. Why they are called imaginary? Because they are not real, no? Not real. Okay, we said that if you are trying to evaluate the negative root in R, there is no negative root in R. Okay? So negative roots are not defined as real numbers. So that's why mathematicians always find solutions. Admit not always straightforward, but so they said, well, this is negative 16 under the root is just equal to negative square root of 1 multiplied by 16. That means here, if we solve the problem with this root of negative 1, we solve the entire problem of any negative root, okay? So if we call this negative 1 square root, they just call it I for imaginary. And they expanded the real numbers to involve. Now here I see some literature, they don't like to use this notation because they say negative roots does not exist or do not exist. But this is, of course, equivalently to I squared equal negative 1, okay? Now, they define the complex number, set of complex numbers as follows. Call it C equals the set that contains X plus I, Y, such that, so maybe I close this in parentheses, X and Y are real numbers. So you see directly that the complex numbers or the real numbers are always subset of the complex numbers because they are defined. Or you can equivalently use I squared equals to negative 1. Okay, now this component here, we call it the real part. This one here, only Y, we call it the imaginary. So imaginary part, and so it has two components, real component and imaginary component. The real component is always without I, the imaginary component is with I. Yes, please.
It's not C complement or one.
It's C, but it's just this is C with a dash somewhere, just to distinguish. It's just like we did it for R and N, you know. Okay, so it's just symbol for the complex numbers. Now, notice that we can have some numbers. We said that the real numbers are, so maybe here I will just write it as a note. R is a set of, a subset of C, right? Yeah. R is subset of C because every real number is just like Z is a subset of Q, for instance. Every real number, we can write it as, for instance, if we take 5, we can write 5 plus 0i, okay? So it's in C, okay? So any number, real number. So this is what we call pure real numbers. So real numbers that don't have any imaginary component. On the other hand, we might have numbers that have pure imaginary values. This is also, this could happen if you have like the number we just evaluated up there. According to this notation, what is the square root of negative 16?
4i.
It's 4
I.
I, yeah?
Yeah.
So I, and then square root. So actually it's plus minus for I. Okay, now we are going to give the real number here, maybe Z. So we are going to use Z as a general number here, X plus IY. And we are going to take X or real part of Z or EZ equals X and IM of Z equals to Y. So just to refer to these two components, imaginary or did I use here IMG? Or, okay. It's just a notation. So whenever I have a number in C, I am going to use Z, and Z will have a component X and Y. Now you see that anyway, if you have a real number, sorry, complex numbers, then you have two components. You can think about these two components as an ordered pair. But bearing in mind that the X component here is the real and the Y component is the Z component. So that means here we can actually map the complex numbers to the XY plane. And if we just define it as we said before, then we are going to just use it the complex number plane, which is similar to the Cartesian. What is the question here? This is IM for imaginary, and this is, shall we take an example? So for instance, 3 plus 2i, okay? So the real number of Z is 3. The imaginary part is 2. Okay, so this is an example. Now what I was saying is that if I have a complex number, so we agree on the following, that the y-axis is reserved to the imaginary part. So this is the difference. But at the end of the day, you have the imaginary and real component. You can represent them as a, so this one here, for instance, if this is 1, 2, 3, this is 1, 2. Okay, so this is going to be, so this number here is just, so if I agree that Z here is going to represent, sorry, Y represents the imaginary number here, you see there is a parallelity to vectors here. So if this is, I just say this is 3 and 2. Okay, so there is parallel here to a vector. And also there is another parallel thing here is, you remember when we talked about the coordinates, and this is actually when working with the complex numbers, it simplifies things very, 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 we'll see later, very much if you transfer the complex number into the corresponding polar coordinates. And always ask yourself, whenever you have a complex number, where is this located? Remember, we just named these quadrants. You remember? Quadrant 1, counterclockwise, quadrant 2, quadrant 3, quadrant 4, and this one positive, positive, XY, negative, positive, negative, negative, and positive, negative. Okay? So whenever you have a number, yes, please.
Why did we take 2 as Y?
It is the agreement to represent complex numbers into a special, let's say, special Cartesian coordinate system. Okay, it's by agreement. Okay.
If we say I is with X and J is with Y.
No, it's just agreement that the complex, because it will make a big difference. It's just like, I don't know why when you go into a plane they name the seat 3G or whatever. Yeah. If you go to a movie theater, maybe they call it different. Okay, so it's just agreement. But this is good question actually, to just make sure that the imaginary axis is the y-axis. This is how we implement. Okay, and the real axis is the x-axis. Okay. So always, wherever you have this number with I, it's the y component. Okay, even if it's written the other way around, or if you just have a number. Yeah. For instance, here, if I ask you, where is the number? Let's say this number here. This is 1, 2. This is negative 2i. Okay. This is here positive 2i. This is here maybe negative 3. This is positive 3. Okay, so the coordinate here of this point here is 0 and negative 2i. Okay. Now this z here, it can be also evaluated as the polar coordinate. So notice here, remember that this theta starts with the positive x-axis. So if this is theta and this is the let's say the magnitude of z as a vector. So in polar coordinate, if we have a number x plus iy, this is what we call standard coordinate, standard form. We can transfer it into polar, right? And remember what we needed for polar form. We need the magnitude and we need theta. Again, here the magnitude is straightforward. The magnitude of z is equal to x squared plus y squared, all under the square root. Similar what we did with vectors. And theta is arctan or tangent inverse of what? It's just like we evaluated of y over x. And also bear in mind here, if you get a negative, then just like we did before, if it happens to be in the second quadrant or third or fourth quadrant, it could be the same ratio here. Yeah? I hope this is clear for everyone. So for instance, if I have a point, for instance, if I have z1 equals to 3 minus 4i and z2 equals 3 negative 3 plus 4i. These are two different complex numbers, but if you just construct this ratio, you will be getting the same ratio, right? How to distinguish which one belongs to which quadrant? Just consider the coordinates. So this is x, this is y. X positive, y negative. Which quadrant is this one? Positive, negative. This is in quadrant. This one is in quadrant 2. And ultimately, the value of the angle will be also dependent. So that's why at the beginning, ask yourself very primitive question. To which quadrant does this order pair that represents this complex number belong? After you answer these questions, you will be doing your calculation at the end. If you got a negative angle, that means it's from the x-axis up to this line. So if it's negative in the second quadrant, means it's this. Remember, negative means it's counter the rotation direction that we agreed upon. So we agreed upon that this is starting here. This is our positive rotation for the angle. If you get negative here, that means it's the shortcut here. So asking yourself to which quadrant the number belongs is important, because ultimately you will be doing your analysis. I see sometimes that students say this is in quadrant 2, and then they tell you that the angle is 330. Here the angle is between 0 and 90, here between 90 and 180, here between 180 to 270, here between 270 and 0 or 86. And in terms of what you call it, the radian, 0 to pi over 2, pi over 2 to pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi. Okay. So evaluating the corresponding polar coordinate is important. There is another very important coordinate, and sometimes it's even easier. It's called the what is it called? The it's Euler's coordinate. I think it's called No, the coordinate, it's called something like let me check it. Anyway, it's not here yet. Exponential, I think it's called exponential, because E is always raised to some power. I think it's called exponential. But for now, let's see some. It's exponential. It's just e to the power or e to the power I theta. Now remember something here, that we have here to deal with different arithmetic when we talk about complex number. So that's why we will talk some operations regarding complex numbers. As you might expect here, okay, operations on complex numbers actually. The operations, first of all, if you have a complex number and you multiply it, you will see here that there is lots of parallel behavior, like we had with no, not with real numbers, but with vectors, okay? Okay, so given complex numbers, let's just call them Z1 and Z2, where let's break each one down to its two components. Z1 equals X1, its real component, plus Y1 times I. It doesn't make any difference if you write I before or after, but sometimes we write it in this order is better. Z2, it has X component X2 plus Y2 times I. Okay? Now, if I multiply, and let's say K is a real number, then K times Z1, let's say, equals to K times X1 plus Y1 times I. And this is as you might expect it, like multiplying a scalar with a vector. So you need to multiply it component wise. Okay. So here we multiply, then the result here is Kx1 plus Ky1 times I. Okay, let me give you the operations here with example here. Let's take a very simple example. 3 times 2 minus 4i is equal to 6 minus 8, no, 12. Right? So just we expand the coefficients. This is very simple operations. Now, addition. Now, maybe here at the beginning, I'm just going to distinguish addition. So Z1 plus, let me just use this symbol, then later we just use. So this means X1 plus I times Y1, or Y1 times I, plus X2 plus, sorry, I just placed this Y, this I here in the back, doesn't make a big difference. Okay, what we do here, it is done component wise. So I add the X component to the X component and the Y component to the Y component. So this is equal to X1 plus X2 plus Y1 plus Y2, and this is multiplied by I. Notice that I here, it appears only once. So I add the X components up together and the Y components up together. So this is how the addition is defined. So sorry, I hope it's not confusing. Here you have the I, here you have the I. Okay, so let's take an example here as well. So if you have 3 plus 2I so this is equal to 3 plus 1 plus 2 minus 4I, and ultimately have 4 minus 2I. Okay, so component wise. Subtraction is similar. The only difference here by subtraction, you need to remember that this one here is commutative. That means here, if I just flip the order of Z1 and Z2, this will not do any harm to the output, right? However, if you have subtraction, then the order matters. Z1 and Z2 must be in the correct order. So Z1 minus Z2. Here again, we do it component-wise. So you have X1 plus Y1I minus X2 plus Y2I. And this is equal to, let me just do it here down, X1 minus X2 and minus X is it minus or plus here? Should be plus, right? Should be plus. This one here plus, because you have here, you subtract the y's here, so y1 minus y2 times I. Okay, so here again, notice that here this is the imaginary part of the outcome. This is the complex part, the real part, and so on. Okay, now it gets more complicated. Shall we take an example here? Let's take an example with subtraction. Let's see, 3 minus 4I minus 2 plus 5. This is equal to 3 minus 2 plus here minus 4 minus 5 times I. It's 1 minus 9. Okay, so addition, subtraction, actually straightforward. It's not that complicated. Multiplying with a scalar or a constant, it's also straightforward. Any questions so far? I always forget the students online. I can't. Okay, always measured and yeah, it's always measured anti-clockwise. So if you get, there was questions regarding the angle. If you get a negative sign, it means it's close to the x-axis, shortcut to the line connecting the origin and your point. Okay. Is the angle measured from negative y-axis, negative imaginary? The angle is measured from positive x-axis, but if you have it in negative, it will be the opposite. That means clockwise. Okay. We will demonstrate this in the tutorial. I hope that will be clear. If not, just please ask there. Okay. All right, so now it gets a little bit more complicated, multiplication and now multiplying complex numbers. Before that, I will remind you with some school mathematics. Okay, so if you multiply x plus 2y multiplied, yes, you can see, multiplied by 2x minus 4y. How you do this?
X times 2x. 2x.
So you multiply this x with this and with this one, then you multiply y with this one and that one, right? So all in all, how many times you will be getting there? You'll be getting four times. So here the middle term will include x and y, so maybe you can add them, they will be homogeneous, so to speak. So you end up with having three times. Here multiplication is similar. Multiplication is similar with okay. So we assume that z1 is equal to x1. So if I just want to multiply z1, so let me use this asterisk for the multiplication. So here x1 plus I or y1i multiplied with x2 plus y2i. Okay. Let's evaluate this. Now, as the formula here up there, so who's going to tell me the first? What will be the first entry here in this multiplication? X1, X2, right? And notice that this here in between is real number multiplication. Okay, so that's why maybe I use dot here. Plus X1 times, okay, X1 times Y2I. Okay. Now then we come to y1i, multiply it with, okay, I can just write it x2 y1i plus, what is the last term? y1 I times y2 I. And this is equal to y1 y2 I squared, right? Granted? So everyone agrees? Now here, look, here the difference here in complex number, what is I squared here in complex number?
-1.
This is -1. If you multiply it with y1, y2, all this will become minus y1, y2. Okay? Not only that, this one here will go to the real part of the result here of the multiplication. This is something unique for complex numbers, okay? So here again, y1 I multiplied by y2i will result in y1 y2i squared, but I squared it's -1. So it is a real number, so it goes to the real part here, okay? So this is a real part, so it goes to this part. So now if I just so to speak, group the alike terms to split the real and the imaginary parts here, I end up of having x1, x2 minus y1, y2, which is the real part of the outcome here, plus x1, y2 plus x2, y1. This is all multiplied by I. Okay, so this is the outcome here. So this is here the real number of z1 real part. This is the imaginary part of z1 z2. Okay, so in other words, if I want to multiply two complex numbers, I multiply the first real component with the second, subtract it from the first times the second imaginary component, and then here alternating x, y, x1, y1, x2, y2. Oh, thank you. There's some shade here. Thank you very much. Okay, any question? You're welcome. Any questions regarding complex numbers, guys, online? What time we have the break now? A minute ago, no? Okay, I just want to stick to for the breaks because some colleagues are complaining because of the voice and the noise. So let's stop there and we will continue with the example after the break.
We're done now, right? That's 12:15, right? Yeah. So 1 hour. Well, we stack up the stuff, right? So, until now, I didn't learn anything new in mathematics. Yeah, but now I know three ways to solve it, you know?
Next class, right?
Today's not, today's structural engineering, new things tomorrow.
Yeah. Today. Until 5:15,
Engineering mathematics,
17:15.
no, finish it tomorrow.
Sorry for the disappointment. I thought the same at first. But then I woke up realizing, oh, whole day.
I have joined the one with the big seat. Yeah, it was finished, yeah. I just saw the notification. I thought, oh, okay, we don't have to distribute it.
Tomorrow, we want to camera. Tomorrow we have like one mathematics tutorial.
That's not soon.
Okay, but
What do you want?
every morning it's okay. For 1 hour. today. Yeah. Today is,
Okay, guys online, do you have an access to? Barely could hear you from my end here. Now you can hear me? Can you hear me now? Better? All right, so we are going to solve together as we did last week. Actually, we said that there's a group on Thursday morning for the tutorial. So if you prefer to attend tomorrow morning, just check the schedule. And there's also a change, as you know, next Wednesday, I think it will be a holiday here in Germany. So 1st of November here in Germany is a holiday. Not in Germany, actually. I don't know whether it's for all Germany, but in Bavaria for sure. So make sure that you go shopping on Tuesday for 2 days. And there will be no classes. So that's why Mr. Wolfgang and I from the informatics, we thought of shifting the classes to Thursday. So alternating, so just check the schedule. So IE and ESE classes for next Wednesday will be moved to Thursday. Okay? So Thursday you have informatic usually, but this November 2nd, we'll be having mathematics. Now, November 8th, it will be the opposite. So you will not be having classes on mathematics on Wednesday, but Thursday you will be having informatics, okay? So that's why please update always the schedule from the website for the latest.
Next week.
So next week we are going to meet on Thursday, okay?
And then Wednesday.
Wednesday is holiday. Alle Heiligen. This is the day, if you are not familiar to German holidays, where they remember death and dead people, relatives. If you go to graveyards, you will see too many, candles. It's called Alle Heiligen.
26, we have the other class from 9:45 to 1.
So, okay. Guys online, do you have access to worksheet number 3 from Ireland? So it's entirely dedicated to vectors. Now here I thought in the first assignment, it's not much to do there, but if you see here, I underlined points, or it's bold there. It means here I'm giving you coordinates of points. So you need to evaluate the vectors. And there, remember the tool, the rule, subtracting head coordinates minus tail coordinates, okay? To evaluate the vector.
Can you repeat that, please?
Well, let me just, thank you. Let me just show you something here. These 2 points connecting, so 2 coordinates. So this is P1, let's say, or A, with coordinate X1, Y1, Z1, right? And this is B with X2, Y2, and Z2 coordinates, let's assume, okay? Now, if I construct the vector connecting both, so this is here the tail of the vector, no, this is PA. Here, so this is PA. So the vector connecting P as a tail and A as a head, its coordinate is as a vector here. I evaluate this vector BA as X1 minus X2, Y1 minus Y2, Z1 minus Z2. Okay? So here you are not given a vector, you are given coordinates, and you want you need to find out the vector, okay? You got it? This is what we call the position vectors, I think it's called. Here, be careful to the negative, etc. And as soon as you evaluate the vectors, then you can proceed with the magnitude and so on. This one here is just comprehensive to what we did today. I think here I just want to give you. I see here we didn't talk about the projection, right? Mm. So maybe here I want to give you the formula. And so this is equal to projection of A and B. It's equal to A and B. So this is the formula for the projection of vector A on B. Okay, so notice that here B here is the second here in the formula. So it's defined as the dot product divided by the magnitude of this one here down multiplied by B. So this is the vector. The scalar projection is only this one here. Okay, if you started with question 2, it's actually sums up what we did today in the first session. And let me know if you need assistance. And of course, as always, you can work in small groups without disturbing the others. Yes, please.
For the scalar product, we need to use the product vector, the product of vectors.
Which part talking? Question 2?
The first question, scalar product.
Scalar product.
Just
First
have to
question, there's
multiply.
no scalar. Is there multiplication in the first question?
Yes, I think I figured it out.
It's only the magnitude, no? You mean second question, first part, right?
Yes.
Yeah, you multiply component wise and add them up. Okay, you got it? So you want to multiply A and B, so you multiply. So here, what is the component is -1, multiply it with 3. Add to it 2 multiplied with 4, and so on. You got it?
All right, then. That's for the second question?
For the second question, first part.
Okay.
Okay? You got it? So if it's easier to you to translate this IJK notation into triple, so notice here that this vector A, actually, if you want to write it as triple, it's -1, 2, 3. B is 3, 4, 5, and C is 2, -2, and 7. Okay, so dot product here, component wise multiplication and adding them up.
Right.
So scalar product A and B,
3, 8, 15.
-3 plus 8 plus 15. Okay, 20, right? No. Yes, please.
So the magnitudes, if I have like AB, I just add them up, yeah?
Yes, you multiply component wise the x coordinate with x coordinate added to y times y, c times c.